Okay, so we're reading the example on pond ripples in 2.6.
What is this?
So it says something about a pebble being dropped in a calm pond. You guys have done that, I'm sure, many times, right? Or skipped stones. And the ripples, they form concentric circles. And what happens to those circles over time? They expand, right? So we're going to now do one of my favorite things in Calc 1, which is called related rates. So we're going to be able to relate like how the expansion of those ripples occurs in terms of area and radius and all kinds of different things. Anything we possibly imagine almost. So how do rates that change in time, that's the key. We're going to be looking at changes in time. So when we take derivatives in this case, because derivatives are rates, aren't they? They're like slopes, which are rates. They're instantaneous rates. They're instantaneous rates of change. And we're going to be differentiating not with respect to x or with respect to y, but with respect to time, so that we can get something that changes over time. Okay? So in this one, it says you drop a pebble, the radius of the outer ripple is increasing at this much. That's some kind of given piece of information. When the radius is 4 feet, so once it gets out to 4 feet, how fast is the total area changing? Okay? So there's a very specific kind of process you can go through to make these problems easier for yourself. So I'm going to kind of just do it on this one, and then we'll say what the process is to help you. Okay? It's like a 4-step process. And I think mine's slightly different than the book. So the book does it pretty good though. Anyway, so first, every time when you have a problem like this, first you should sketch what's happening. Okay? So I'm going to sketch what's happening. We've got circles, they're concentric, right? They're growing outwards, so you might kind of put some kind of vector arrow to represent how growth is occurring. You know, just something that makes sense to you. But you do need a sketch. You will see that that's necessary. So absolutely, no matter what the problem is, try to sketch it. What's up? I'm sorry, Sheldon.
A.J. Hall, Zach Reedhead, and Pete Williams to the administrative office.
It'll be on the video. I'll video it.
You feel like a gangster riding this, Mr. McGee? As it's a precinct,
I guess so. I did make this one, so I was probably mad that I couldn't get stuff to work, so I wasn't concerned with the English, making these kind of a pain. Anyway, so that's the sketch. The next thing that I like to do is write down my given info. This is really, really important for these kinds of problems. So what kind of info did they give me? And I need to label it very correctly. So what do I have here? I have that r equals 4 feet, right? What else did they give me?
1 feet per second? Or 2 feet per second?
They gave us that, so that's 2 feet per second. When you write something as a fraction like that, that should clue you in. This is a rate of change, otherwise known as a derivative. So I should be labeling this with a derivative. It's how fast what's happening. It's how fast the radius is changing with respect to time. You guys starting to see why Leibniz's notation is kind of superior sometimes? Because if you just put r prime, that doesn't say anything about time. That's why it's a little bit more mysterious. So Leibniz can be beneficial. Okay, so I'm going to call this the instant info. We are not going to touch this info until we're done with the problem otherwise, okay? The next step is can we somehow from our diagram come up with a primary equation like for optimization that describes what's happening? Oh, and I guess I should ask this too. What's the question asking us to find? So key. You want to write that down every time and make it easy for you. What are we asked to do?
Right. The change in the area.
So what is that called?
Total
dA
area.
dt.
dt. What is dA dt? See, this gives you a big clue that the primary equation we should work with, if you didn't get it from your circles over there, is area of a circle, right? So the primary equation that we're working with is the area of a circle, which is of course what?
A.
2 pi r squared.
Oh.
Pi r squared, right? So what do you think we're going to do with this equation for area of a circle? If we want dA dt, what should I do? Take the derivative of a, but not with respect to r, with respect to time. So I'm going to take derivative of a with respect to time, because they asked me about time. They didn't ask me about some kind of radius. And what's the derivative there going to be? Pi is constant, so we go 2 pi r, right? But remember, we took the derivative with respect to time. So what else has to go here? The chain rule has to go there. Now remember, if we had taken the derivative with respect to r, think about it. You'd get 2 pi r times dr, which would be 1. But this time, we're taking it with respect to time, so that doesn't just go away as 1. Does that make sense? And then finally, once we've gotten this down, sometimes you can solve it for what they're asking for if it pops up somewhere else over there, but this one's already done. Now we can finally say, okay, at our instant in time, when the radius is this big and it's increasing at 2 feet per second, what's it going to be? And we can plug in our stuff. Okay? It's all there, isn't it? So we can say, all right, so dA dt is going to be 2 pi times 4 times, it's increasing, so it's a positive 2 for the derivative of the radius with respect to time. So we get what? 8, 10, no, not 10. 16 pi units. You've got to watch your units on this always, they'll nail you, and so will I.
Feet squared first.
Look at this. Area is feet squared, time is seconds. Does that make sense? And then the last thing that I'm going to insist on is that you write out what you found, because that's going to be necessary for you to clarify sometimes. So how can we say this?
The area is,
Go ahead, Paul.
the area changes at a rate of 16 pi feet squared per second when radius is 4.
Yeah, that's good. I like that. So I'm going to say when the radius of the, we've got ripples happening here, right? So which circle are we talking about?
The outer one.
Of the outer circle is 4 and increasing, so that radius, you can put radius again, increasing at 2 feet per second. The area enclosed by the circle's total, right, defined by the outer edge, is increasing at 16 pi feet squared per second. So we've already answered our question. Let's go see if maybe the graph confirms that. So I've made a little applet. That's the idea. So let's go see. I think we'll just leave the applets out for the rest. I have too much time to mess with them. Let's see. So here's the thing I made. Let's see if I remember how to use it. So there's one circle. I wanted it to show like multiple layers. So let's see if we can
see this.
I just said, but that's $1 penalty on my head because I stole someone's car.
Like every where's this going? Yeah, I did that too. I got 3,000.
I had 350, so I got one spreadsheet by dollars. Because I blocked him.
Just like the army.
Okay, so let's see if we can figure out what's going on. Can you guys see the circles increasing? That makes sense, right? That's nothing we weren't expecting. So it's tracking how the area is changing. Which one of these things do you think is which? What are these two graphs over here plotting?
The top graph is just the constant of radius.
Because it's increasing at a constant rate, right? Do you guys think that that's actually true when you throw a rock in the water? Let's think about it. If you throw a rock in the water, do you think those circles increase at a constant rate from when it hits the water to when it's kind of like petered out? It might be like slowing down, so is that a necessarily safe assumption? It's kind of like we're making it ideal in this case, right? So this probably might not be constant. What's this thing down here tracking? Just the area? The rate of change of the area, right? So if we had said not at the instant when the radius is 4, but if we move to like the instant when the radius is 8, is that area changing at the same rate? No, notice, like if it was 4, it might be right here, but then when we have a much larger circle, it's like way out here. What's happening? So let's let it start over. Wait, come on. Okay, there we go. So right now, the area is not changing that much. Does it make sense? Like the area is not changing that much right now because it's pretty small still. But once it gets out here, even though the radius is still going at a fixed rate, what's happening to the area?
It's getting a lot bigger faster.
Does that make sense in this situation? Like once you've got a big circle, if that radius is continuing to go at the same rate, the area is getting bigger a lot faster. That's why it's at a higher value here. Does that make sense? Okay. So sometimes it's hard to think about these, but don't skimp on the thinking or they'll be a little tougher. You can still sometimes get them without thinking too much. Anyway. That's the good part. So let's get this thing turned off. Let's do one more today. That's one more.
Brian, your back's looking a little dry there.
I didn't. This is it.
Okay, guidelines. Steps you should be taking on every one of these.
You have portables in your
You guys ready? I'm gonna write stuff. I'm gonna write stuff.
Give that. Give that. Austin.
Todd's pencil?
No.
Yeah.
Well, that one is.
I don't know.
It's on.
Okay, step 1 is probably the most important. Many of you are going to have trouble with this because you're not spending enough time doing step 1. Sketch it well. Label the stuff well. And most especially these two things. What did they ask for? Put an appropriate label on it. Did they ask for dV/dt? Did they ask for d voltage dt? Did they ask for d llamas dt? I don't know. Okay. How fast the llamas are entering the zoo? I could ask something like that. It could happen. And then, what is the instant info? They're always going to give you some info that you are not going to touch until the end. You never use your instant info until you're done with everything else. It's just stuff to plug in at the end. Okay?
Is there
Step 2. Yeah.
Is there going to be parts where there's like 2 equations like we were doing with optimizing?
Yes.
Yeah.
Usually not on the AP exam, though. Usually they ask you one that has 1 equation. Maybe 2 sometimes. We'll see. Okay, step 2 is take a derivative. Differentiate primary equation with respect to time. dp dt. Always time when we're doing a rate. Okay, finally, sub in the instant info. Sometimes you might want to solve it and make yourself happier about it first before you sub in the instant info. That's up to you. It can work either way. You solve for your desired thing that you wanted there. I guess I'll put that. Solve for desired. And then finally, I know you guys are not used to this because I don't even require it all the time, but I'm going to here. You need to write out your solution in context. That means a complete sentence that describes exactly what you did. Calculus test is going more and more towards that, and I've seen them starting to give points for like a written out solution. You don't want to miss a point just because you didn't write it out. It's dumb. Okay? And I agree. You should know what you did. So one complete sentence is plenty for that. Okay, so let's do one more and let's try to follow this process.
Yes. Wow. Wow.
You want me to take that?
Okay. So I'm just going to say this out loud, so you don't have to pay attention too much. Okay, so let's say we have a sliding ladder. This could be very applicable. I've had this happen to me before, where I'm on top of a ladder, and for some reason it gets dislodged at the bottom, and it starts to slide down the wall. So that can be ouchy, it can be bad. So it might be something good to know about. But anyway, interesting problem. A sliding ladder. So I'm going to picture it like this. We've got some kind of building. Let's lean a ladder up against that building. Here's the axis. And let's say it starts to slide. So it's starting to do this up there. Where's this going? This way or left? Left or right? That end right there is going to the left. I'm sorry, my ladder's not perfect. Maybe it's because I have brain damage from the time that I fell off a ladder like this. I don't know. The ladder stays fixed though, right? The length of the ladder is not changing unless you're thinking it's bending or something. We're not going to say it's bending. It's like staying fixed. What's changing is these distances. This is a y. This is, of course, an x. So here's what I'm going to tell you is the situation. Let's see if you guys can pull out the stuff. A 10-foot ladder leans against the side of a building, so I should probably label that 10. If the top of the ladder begins to slide down at a rate of 2 feet per second, so let's start labeling our stuff.
Wait, is that the ladder?
Yes, sir.
Is that a 45-degree?
I don't know, I haven't told you yet. So I did say if the top of the ladder begins to slide down at a rate of 2 feet per second. How can I label that? What's that mean? Top of the ladder is dy dt. That's this part, right?
It's negative 2.
I said 2 feet per second. Austin?
Negative.
That's negative because it's going down, right? We want to have correct coordinate system here. Okay, so that's one thing. The question is, how fast is the bottom sliding away from the wall? That's what's happening, right? Like it started right here and it's like sliding that way. So how fast is that happening when the top is 8 feet off the ground? I told you two things there. How fast is the bottom sliding out when the top is 8 feet off the ground? What did I tell you?
dxdt?
We want dx dt, don't we? There we go. That's what we're searching for. What else did I say though?
No.
8 feet.
What's that mean?
X equals, or Y equals 8.
Yeah, I think that's part of that's the instant in time we're looking to investigate eventually. But remember, you're not using this stuff until you're done. You can look at that and say, hey, that's a clue. Maybe that'll help me build my primary equation. What do you guys think? What would be a good primary equation to somehow get x for this situation? I don't think it's going to take rocket science on very many. There's a couple tough ones I gave you, but most of them, primary equation's not very hard. How do you figure out x for this? Yeah, Pythagorean theorem. What is the Pythagorean theorem for this triangle?
1 of 10 squared. 8 squared.
You're using the instant already.
Y squared.
Don't do that.
Y squared.
No.
Thank you for doing it though, Paul. You showed them something that's valuable, right? You're not touching that instant stuff till you're done. There's like a triangle in here, and this leg of the triangle from here to here is x, and this leg from there to there is y. Does that make sense? Okay, so there's a primary equation. Second step, do what to it?
Solve it.
Differentiate it with respect to time. So derivative of 100 is,
0.
derivative of that is,
dx dt.
there we go, our chain rule. Derivative of that is,
Why do we have dx? Because it's not respect to x.
it's not respect to x or y that we're taking derivative, it's respect to time. So you've got to use that chain rule. Once again, if you had that one from a second ago, and you take the derivative of this with respect to r, it's 2 pi r dr dr. We don't write that because it's 1. But if we take the derivative of that with respect to time, it's 2 pi r dr dt, and we do have to write that. That's the difference. It's a good question. Okay, so what are we supposed to solve for? So solve for it. Dx dt equals, move that over, that's negative 2y dy dt over 2x. 2's canceled, so you get negative y.
I did just move
X.
over dx dt.
That's 10.
He actually subtracted 2y dy.
I moved this over there.
By 2x.
You do it how you
Oh,
like.
okay, I see.
Use your favorite algebra, I don't care. So now, stuff in, and we should get our answer. Hopefully it makes sense too, right? Like our coordinate system, it should match up with that. So if I go negative 8, dy dt, we were given that was negative 2, right? Were we given x? Do you see x over there in our list of stuff? So this is where a lot of the time when you're plugging in your instant stuff, you kind of have to redraw your picture. I'm going to call this the instant picture. You don't have to, I mean, if you can do it in your head, but it's helpful.
Because you know the ladder's 10 feet tall. and
At that instant, the ladder's still 10, right?
So it'd be 6.
And at that instant, this is 8.
So it'd be 6.
So we need to know what x is at that instant, which is a Pythagorean triple in this case, isn't it? So 6. Does that make sense, though? This is the instant picture at that very instant in time they asked us to investigate. So then we simplify and we get, oh, I have one mistake too.
Yours says negative 8 feet off the ground.
Isn't that negative the way I have my picture drawn? It's not a big deal, but that is negative if I've got it in quadrant 2 like
Can you
that.
just draw your picture differently?
I could. But it should match our picture, our answer. So anyway, what's this going to become? 16 over 6 negative? The way my picture is drawn, isn't that pointing this way? So it should be going that way at this rate.
With
dx
positive on
dt.
top.
It would, but over negative is...
Right, okay, so you just...
I'm just saying it should match your picture, okay? It's not a big deal. Units. Feet per second. Because that's a length. Good. And then we'd write it out in a sentence. I'm not going to because I'm dead. I need to take a break before philosophy, so. So we'll do a couple more.